today's carbon-based fuels. While addressing these divergent challenges seems to require completely different skill sets, there is one thing they have in common. Solutions to all of them are being imagined, researched, and tested by nanoscientists. Solving these problems may not be within the grasp of today's technologies, but continuing improvement in the sophistication we have in dealing with structures at the nanoscale makes many scientists optimistic that solutions are forthcoming in their lifetimes. There are a number of try-this-at-home activities included in the materials for this course. I want to emphasize that some of the truly fantastic science that we discuss here is not science fiction, but science fact. The scientific theories and laws we discuss have all been discovered because scientists carefully observed physical reality under highly controlled conditions. They formulated and systematically tested hypotheses and continually revised their models and theories. If you have the opportunity to try things at home, pay attention to the details of the experience, and it will allow you to have some insight into the excitement of scientific discovery. We'll begin this course with an introduction to the metric system of measurement. In most of the world, the introduction to the metric system would not be required, because in most of the world, the metric system is the common system of weights and measures, and it is familiar to all school children. But the metric system is still not familiar to most folks in the U.S. Here we still use what's called the English system of weights and measures. We use miles, feet, and inches to measure distance. The metric system uses meters. We use tons, pounds, and ounces to measure weight or mass. The metric system uses kilograms. One unit we have in common with the metric system is the base unit of time, the second. We'll discuss more about the metric system in Lesson 2. Nanotechnology is extraordinary in that it is a branch of science which was predicted with uncanny accuracy by scientists some 30 years before it was ever realized. We'll discuss Richard Feynman's 1959 talk, Room at the Bottom, which laid out the development of nanotechnology in Lesson 3 of this course. You may recognize Feynman's name for any of several reasons. He won the Nobel Prize in Physics in 1965. The prize was awarded for his development of quantum electrodynamics. Feynman also developed a pictorial representation method for illustrating the sophisticated mathematical expressions governing the behavior of subatomic particles. These illustrations are now known as Feynman diagrams. But Feynman is most likely familiar because he was a serious educator and a popularizer of physics. His series of lectures delivered between 1961 and 1963 to first-year undergraduates at Caltech, where he held the Richard Chase Tolman Professorship in Theoretical Physics, were aggregated and edited and had been published in a variety of formats as the Feynman Lectures on Physics. Lots of physicists still refer to the Feynman Lectures on a regular basis as they work through their problems. Feynman was interested in science writ large and also interested in conveying the excitement of the new ideas in physics to sophisticated audiences. Feynman's name became familiar to a younger generation when he served on the panel that investigated the Space Shuttle Challenger disaster. His Room at the Bottom talk was given at an American Physical Society meeting at Caltech in December of 1959. In part, it evidences Feynman's breadth of interests in that it challenges chemistry to control reactions on a truly atomic scale. We will discuss his talk as Lesson 3 in this course. In Lesson 4, we'll discuss why size matters. This lesson will introduce some physical consequences of small size. Those who have read Gulliver's Travels know that author Jonathan Swift sends his title character to the lands of the Lilliputians and the Brobdingnagians in his first 2 chapters, and investigates the consequences of a normal-sized being living in communities where the local scale is either 1/12 or 12 times the size of the main character. The advantages and challenges that Gulliver faces in Lilliput and Brobdingnag do not begin to approach the advantages and challenges of dealing with nanoscale systems, but at least Lilliput motivates us to begin thinking in the right direction. The physical systems that we deal with every day, cars and bridges, balls and bats, airplanes and trains, all obey classical or Newtonian mechanics. The forces that maintain their structures are well understood by engineers, and their movements are described by Newton's laws. A body in motion stays in motion. A body subject to a force